Hello everybody. So in this video we're going to discuss one very famous application of the fluid statics, which is the YouTube manometer. So the YouTube manometer, it's a pressure difference measuring device. So it's a device that we use to measure the pressure difference based on the relation that we know from fluid statics, that delta P equals rho G delta Z. So this is the main basic idea on which the YouTube manometer is built on. It's very simple, yet it's a very efficient way of measuring the pressure difference that can give results very quickly. So to understand it, we will discuss a couple of cases to understand how it works. So the first case is a tube that has a U shape, and this is why we call it a YouTube manometer, because it takes a U shape. So it's a tube that is U-shaped, and it is open from both sides, and we fill it with a liquid. So what we will expect and what will happen is that the fluid will fill the two sides so that the two sides are at the same height. Okay, and this is expected because based on fluid statics, what we know here, this is atmospheric pressure and here is atmospheric pressure. So the two surfaces are at the same or are exposed to the same pressure, so they must be in the same height because they are in the same continuous flow. So these 2 points would be, or the two interfaces would be at the same height. Now we will consider another case where these two sides of the manometer are connected to two different containers or two tubes or whatever. So this is a container is at pressure P1 and this is a container at pressure P2, and still we have the manometer fluid or liquid filling the tube, and we know that P1 is larger than P2. The pressure here is higher than the pressure here. So this is a different case because in this case we had equal pressures on the both sides of the manometer. Now we have different pressures. So P1 is higher than P2. So what will happen is the height will differ for the two sides of the manometer. So this side would be higher and this is lower. And this is very intuitive. If you think of it, this is applying force on the fluid from one side, this is applying force on the other side. The tube has the same diameter everywhere, so it means that the force on this side is larger than the force in this side. So the fluid will be pushed from this side to the more than it's pushed from this side. So this is a very intuitive thing. So it's not it's not a strange thing or an unexpected thing. So this difference in height that we see here is a result of the difference in pressure. And based on this relation, we can find the difference in pressure. So the way we do it is by measuring the delta Z. If you have any YouTube manometer, it's either it has its scale, it's like a ruler, it's a built-in one, or you put it over a scaled surface. So there is like a graph paper or something in behind, so that you can measure the difference in heights between the two sides of the manometer. And given that this difference in height is delta Z, then the pressure difference P1 minus P2 can be measured. And it's the same concepts that we applied on the previous cases for fluid mechanics are the same concepts that we are applying, fluid statics are the same concepts that we are applying here, that the 2 points at the same height in the same continuous fluid will have the same pressure. So these 2 points A and B are at the same height, so the pressure at A equals the pressure at B. Pressure at A is P1. If these two containers are gases, then pressure at A is P1, and pressure here is P2, and pressure at B is P2 plus rho G delta Z. Okay, so delta P is rho G delta Z. So it's as simple as this. So you can find the difference in pressure by calculating or measuring the height and substituting in the equation with, of course, this is the density of the manometer fluid times G times delta Z. This gives us the difference in pressure. If you know the pressure of one of the two sides, you can calculate the pressure of the other. The manometer is usually used to measure an small to intermediate difference in pressure. If it's high pressure difference, it might not be practical, because if it's a very, very big pressure difference, then this manometer fluid will be pushed all the way down here and all the way up here, and it can fill or fill the other container, or reach the other container. If it reaches the other container, then it's not working. Usually we can kind of manipulate this to make the readings more easy and more reliable by manipulating the value of rho. If delta P is small, then we use small density, so you'll have a reasonable value of delta Z. If the pressure difference is high, we use a fluid with high density like mercury, for instance, to have a reasonable value of delta Z. So it's something that we can manipulate based on our understanding of our systems and how much pressure difference we expect to be measuring. Now the manometer can be connected in different ways. One of the ways is you can measure the pressure in a container, for instance, and by keeping one of the two sides open. This is possible if this container is at or the pressure difference between the container and the atmospheric pressure is very low. Otherwise, if this has very high pressure, then it will be like a fountain. All this manometer fluid is going to flow outside the manometer. So if it's a small pressure difference from the atmospheric pressure, then we can connect it this way. The very common way of using, or it's one of the common ways of using or connecting the manometer, is to measure the pressure drop, meaning that you have a fluid that is flowing, going into a process or something, and then coming out of this process on the other side at lower pressure. And this is something that we are very interested in, and we will see this later in the coming chapters, that the pressure drop is one of the very important things that we measure. So one way of measuring it is connecting the two sides of the U-tube manometer, one before the process and one after the process, so we can measure the difference in pressure due to the flow through the process. So this is one other connection, and again the same equation, delta P equals rho G delta H if it's gas. I'm ignoring the density of the gas in this case because this makes the idea easier to understand. We will go through the cases if we have liquid flowing other than the manometer fluid. If we have a flowing liquid instead of a gas, we will go through this. But for now, for the gas, we just include the rho G delta H or H of the manometer. There is one other thing that we will come to later, but it's good to mention here. Now, if we take a closer look at this point here, okay, so this interface is an interface between two phases: the gas phase, which is this phase, and the liquid phase, which is this phase. And from fluid statics, we know that the liquid at this point and the liquid at the same level on the other side will have the same pressure, because it's the same connected fluid and they're two points at the same height, so they will have the same pressure. But in this case, the point I want to refer to is when having two fluids and an interface. Of course, we discuss the U-tube manometer in the fluid statics because this fluid is a static fluid. The manometer fluid itself is a static fluid. So I don't care if this is a flowing fluid or this is not static fluid. But what is inside the manometer is a static fluid, and this is what I really care about. So now for this tube, I have fluid 1 here and fluid 2 here, and I can relate the pressure of the liquid surface here and the pressure of the liquid on the other side. But I want to find, or the point I want to make here is relating these two pressures. Pressure at point 1 and point 2. Point 1 represents the layer of the liquid directly below the interface, and 2 is the layer of the gas or fluid 1 that is directly above the interface. Of course, we measure the difference in height when the manometer fluid is stable. It means that it doesn't go up or down. And in the beginning, the two sides are equal in height, and then the pressures change, and then one of the sides will go down and the other is going up. So there is still, there is in the beginning, there is a little bit of motion, and then the fluid stops. So we do our calculations when the fluid stops. There is no change in height. So at this point, these 2 points, 1 and 2, are two different fluids. So the fact of the fluid statics that the 2 points will have the same pressure because they are at the same height, this is not the same fluid. So I cannot depend on this rule to say that P1 equals P2. But we can do something else. We know that this interface is not moving anymore, which means that the interface is at equilibrium, which means that the net force on this interface is zero, meaning that the pressure from the force from the bottom and the force from the up cancel out. So F1 is equal to F2. I'm now doing this balance on this line, on this interface. Okay, so F1 equals F2, and force equals pressure over area, so it means that P2 over A equals P1 over A, and it's the same interface, so it's the same area, so P1 equals P2. So we can say that the pressure on the two sides of the interface are equal, not because they are points at the same height in the same fluid. These are 2 points at different fluids, but this is because that the equilibrium of the interface means that the pressures on the two sides are equal. So this is a point that we will go through in solving problems. So I prefer to mention this here to make it clear before we discuss it later in the problems. There are a couple of things, if I'm not mistaken, that I want to discuss here. Now, if we have a case where there is a liquid, not a gas, in the manometer, like a case like this. Now we want to measure the difference in pressure between P1 and the atmospheric pressure, if this is open to the atmosphere. So to do this, what we can do is apply the concepts of fluid mechanics. We know this is H2, this is H1. So again, we will look for 2 points in the same fluid that are at the same height. So the 2 points are A and B. So pressure at point A equals the pressure at point B. Pressure at point B equals the atmospheric pressure plus rho G H, but this is H1 and the density of the manometer fluid. Okay, PA equals P1 plus rho G H, but this is the density of water and the height H2. Okay, so P1 plus rho water GH2 equals P atmosphere plus rho manometer. Rho M is the manometer fluid density GH1. So we can calculate the difference in densities or in pressures if we want. Given that if we know the values of the densities and the heights. So this is something we can do as well. We ignored this term before for gas containers, because we said that the density of the gas is very small. So if this is not, if it's a gas, and this is why we ignored it before, if this is a gas, then means that this value is very small compared to P1. So we can easily ignore it without affecting the actual values that we should get. There is one last thing here, which is the pressure drop in flowing fluids. This is one thing that we mentioned before, that you can have a flowing fluid and still apply the fluid statics concepts to the manometer here. Again, this is a liquid. Now we can apply the same thing like the previous case. We have here H1 or H and A, and we want to find the difference in pressures between point 1 and point 2. So we will again pick the 2 points at the same height, at the same level, in the same fluid. So it's A and B. So pressure at A is P1 plus rho G, and this is the rho of the flowing fluid, G times A plus H. And here the pressure at B is P2 plus rho of the flowing fluid, A times G, plus rho of the manometer fluid times G times H. Okay, so again, this is P1, which is this, plus rho 1, which is the rho of the flowing fluid, times G times A plus H, and P2 plus rho 2G H, which is this, plus rho 1G. Okay, so we can we can find the difference in pressure by simplifying the equation. This A will cancel this term, and then we can find the value of the pressure difference in this case. And again, if this is a case where the flowing fluid is a gas, then rho 1 is very small, then the equation will go back to the shape that we know, which is rho manometer GH. So this is the last case that I want to discuss here. There is one last thing here, and it's good to mention that in fluid statics we care about the vertical head. We care about the vertical head, which means that a slope like this doesn't make a difference if it's a slope or it is a vertical or a vertical tube upward. So this doesn't mean that we have more pressure drop or more height. When we calculate A and H, we care about the vertical height. So if it's inclined or tilted with an angle, we don't care about this angle. We care about the vertical height only. So this part is equivalent to this part regarding the pressure drop. In the pressure, I mean the pressure head. So the pressure head in this long tilted tube with this connection is equal to the pressure drop in this vertical connection. Okay, so this is the last thing to mention here. I'll stop here, and next time we will solve some problems on the YouTube manometers, and we'll see you then, inshallah. Goodbye.